Hi, I'm Ethan Kwan, and today I'm going to be telling you about the universal law of gravitation and gravitational potential energy. Let's start off with the first thing. So that's going to be the universal law of gravitation. So what I'm going to be doing for this video would be explaining the topic, and then showing like equations and whatever else, and then we're going to be doing some examples. Okay. So, let's get started with the universal law of gravitation. So, what is the universal law of gravitation? Well, basically, if you have two objects, and in this case, let's just say it's the Earth and the Moon. If it is the Earth and the Moon, you can calculate the force between them, and I'm drawing the force as arrows here, let's just label them F1 and F2, and actually, F1 and F2 are going to be equal to each other, but anyway, the force, so we can actually just call both of them force of gravity, both forces, right? The force of gravity for both objects is going to be big G. Now, what is this big G? Big G is the gravitational constant, so it's just a number, and it's a very small number, and I'll show you what it is in a second. Anyway, it is big G multiplied by the mass of the first object multiplied by the mass of the second object divided by the radius squared. Now, what is the radius squared? That's just the distance between the two objects squared. So it's kind of misleading if you're saying r squared, so I'm going to replace that with d squared. That's better. Okay, so what is this G number that I'm talking about? Well, G is equal to 6.6743 times 10 to the negative 11 Newton meter squared divided by kilogram squared. Now, what are these units for? Like, they're not anything you might see somewhere. So, these units are to cancel out the rest of the units, so they only have newtons, right? So, let's calculate the force, the units of this thing. And remember that since this is a force, this part has to be newtons, right? So, let's write our equation here. And let's say force of gravity equals G, right? G is measured in Newton meter squared divided by kilogram squared, multiplied by, and M1 and M2 are measured in kilograms, so kilograms multiplied by kilograms, and then divided by, and D is measured in meters, right? So it's measured in meters, so M squared. So, there's some units to be canceled here. Kilogram squared cancels with kilogram times kilogram, and meter squared cancels with meter squared. So you're left with newtons, which is exactly the result we wanted. So the units all work out. Okay, so let's get back to calculating the force of gravity between the Earth and the Moon. I've looked up the numbers online, and the mass of Earth is equal to 5.97 times 10 to the 24 kilograms. The mass of the Moon is equal to 7.35 times 10 to the 22 kilograms. G is always equal to 6.6743 times 10 to the negative 11 kilogram. Newton meter squared divided by kilogram squared, the weird units. And D, of course, is equal to 3.84, not of course, but like 3.84 times 10 to the 8 meters. Okay, so now let's add all these units and put them into the equation. Let's just substitute all the numbers, and we get this. And yes, 3.84 times 10 to the meter square, 8th meter squared. Okay, so now we can calculate the force of gravity, and let's just do a little bit of simplification. Just squared the meters, got that, combine those two, 2.977, and then we combine those, and we are left with 1.9869391 times 10 to the 20 newtons. That's a little bit over, so I'm just gonna say about 2 times 10 to the 20 newtons. Too many decimal places. Note that if we measured the meters in in kilometers instead, which actually I did while making this video, you would get a completely different result. 6.82 times 6.82 whatever times 10 to the 28 newtons, and this is very incorrect. It's off by 8 orders of magnitude, so don't confuse that like I did. Yeah, okay. So that means the force between the Earth and the Moon is equal to 2 times 10 to the 20 newtons. Now, why doesn't the Earth and the Moon spin around each other then? Because the forces are the same, right? The forces between the two objects are the same. So why don't they just spin around like this? That's because of mass. Just wait for this to finish. This because of mass. The Moon weighs a lot, but Earth weighs a lot more. So, here's a little simulation, and you might notice that the Earth does kind of orbit around the Moon, but the Earth does wobble a little bit, as you can see here. That's because the Earth is way more massive. If we turn down the mass of Earth, like that, what happens is that the Moon totally dominates, and yeah, as you can see. Yes, okay. And then it comes back. It's, as you can see, the Earth is orbiting around the Moon. Okay, so some unrelated stuff is coming here. So one thing that you might have noticed is that both objects, instead of one orbiting around the other, or the other orbiting around the first one, both seem to be orbiting a common center of mass. Like, for example, here, this point is located, drawn with a blue dot. This point is called the barycenter, and this is the unrelated stuff. That's what the unrelated stuff is going to be about. The barycenter. Now, the barycenter is pretty interesting. Here's the Wikipedia definition. So it says, in astronomy, the barycenter, or barycenter from the ancient Greek, but however you pronounce that, is the center of mass of two or more bodies that orbit one another, and is the point about which the bodies orbit. It is an important concept in fields such as astronomy and astrophysics. It goes on to say that the barycenter is one of the foci of the elliptical orbit of each body. This is an important concept in the fields of astronomy and astrophysics. If A is the semi-major axis of the system, R1 is the semi-major axis of the Primate's orbit around the barycenter, and R2 equals A minus R1 is the semi-major axis of the secondary's orbit. When the barycenter is located within the more massive body, the body will appear to wobble rather than follow a discernible orbit. In a simple two-body case, it gets really chaotic with 3. In a simple two-body case, the distance from the center of the primary to the body center, R1, is given by R1 equals A times M2 divided by M1 plus M2, where R1 equals the distance from body 1 to the barycenter, A is the distance between the centers of the two bodies, and M1 and M2 are the masses of the two bodies. Okay, did you get any of that? Me neither. Let's spice it up with a few examples. So, for example, in this example, as you can see, the barycenter is inside one of the objects. But sometimes the barycenter is outside if the smaller one is smaller, right? If the bigger one is smaller than a certain point, and if sometimes the barycenter is right in between, as in this example, and the two objects just orbit one another like binaries. Okay. There's another case where the two objects orbit like this, which is pretty cool. And yeah, it's cool. And the barycenter, as you can see, is located right there. On the other hand, if the first object is really massive, the Berry center won't really change at all, as you can see here. Yeah. So yeah. Yeah, as you can see, it's not really. The big one isn't really orbiting around the Berry center, is it? Okay. So let's talk about. Let's do an example with this. So here's our equation from Wikipedia. We can move the a up to the numerator, the numerator. So it becomes a times m2 divided by m1 plus m2. And if we plug in all the numbers from our Earth-Moon scenario, right? So if we just plug in all the numbers we know, like this, you can check that, verify that works. The Berry center distance from the center of Earth comes out to be 4,670 kilometers. In other words, if you have the two bodies, Earth and the Moon, and I'm just labeling the center of Earth as a orange dot. This is again not to scale. The Berry center is about 2/3 of the way out of the Earth, so right around there. And we can also figure out how far it is beneath our feet. So 6,371 radius of Earth minus 4,670 distance to Berry center from center of Earth is equal to 1,701 kilometers below your feet. So the Berry center is about 1,700 kilometers below your feet, which matches this thing right here that I found just Googling it. Yeah. So let's not do any more unrelated stuff, and let's go back to examples. So here is we're just using a distance of 1 meter. Here is our equation, and let's say one object is a person, and the other object is a computer. And as you can see, they're 1 meter apart. Let's just say that's 1 meter. It's totally not to scale. That's a big computer. An average computer is about 1.5 kilograms, and the average mass of a human is 62 kilograms. So let's input all of these numbers into our equation, and this is what we get. Note that I've left out what the g is, because g is always the same, and after we do a little bit of calculating, 93, multiply that, and we get that it is 0. Lots of zeros, 6207099. Okay, that's a little bit hard to read. So let me rephrase it in scientific notation. That is still hard to read. So turns out that the force between Earth and the Moon, a person and the computer is very, very, very small. It's there though, so that's something. So that means the force between you and the computer screen you're viewing this on, it kind of depends on what kind of computer you are viewing this on. The force between those two objects is 6.207 times 10 to the negative 9, which is pretty cool. Newtons, of course, which is pretty cool. Okay, here are some other numbers that you might be interested in. So, yeah. Note that I did not calculate the last one. I just got that off Google, so thanks, Google. Anyway, now let's talk about the next thing, gravitational potential energy. Now, to understand gravitational potential energy, we first have to understand potential energy. What is potential energy? Now, potential energy is basically, well, in this case, gravitational potential energy, but the most used example in potential energy is if you lift the mass off of the ground, the potential energy is equal to, of this object, is equal to m, the mass of the object, times g. G is the gravitational is the force of gravity of Earth, and h is the height you lift it. So first of all, we're assuming that this g here is a constant, but what happens if you lift it really high above the ground, like this example? That the gravitational force will go down because it's really far away. So, how do we fix this? How do we get like a general number to calculate this gravitational potential energy? Well, what we can do is we can use Newton's law of gravitation. Again, just recapping, M2 and M1, this is the force between them. So if we want to get the force relative to M2, right, if we just want to see the force of M1 attracted to M2, what we can do is divide both sides by M1. And let's do a little bit of simplification here. There we go. Note that F of G divided by M1. Note that force is measured in, the force of gravity is M times G, right? Because the force of gravity is the mass of the object multiplied by G, right? So all we have to do if we divide both sides by M1, what happens is we get rid of the M, and there you go. Okay, so what we can do now is, this is our equation, right? So this is G. Now we know what G is. It's this thing, right? So what we can do is we can take this equation, PE equals M1G M2 divided by D2, D squared D. Now, where did I get this equation from? I just used this equation up here and just transferred it over. So as you can see, M is M1. G is, we figured what G is, right? G is this thing. So I just plugged that in, and then H is D. So that's how we got that equation. Okay, as you can see, we can cancel some units here. D squared cancels with D, so we're left with PE, potential energy, is equal to G times M1 times M2 divided by D. Now, notable differences here from gravitational force, because it looks very similar. The D squared is not squared, and also annoyingly there is a negative G out front. Why is it negative? Well, partly to annoy people who are trying to study, but because the farther you get away from something, the more gravitational potential energy you have. So if you put a negative out front, it all works out, right? So if you get far away, it approaches zero, but it gets less negative as it approaches zero. It might help with this. It might help to explain with this graph here. So the y-axis is gravitational potential energy, and the x-axis is the distance from Earth's center. You probably have seen this graph if you've studied gravitational potential energy, but yes, so this is the graph, and as you can see from here, you can clearly see that the gravitational potential energy is increasing as you go farther and farther. But it does approach zero, which is interesting, but yeah. Okay, so let's figure out what the potential energy of the Earth-Moon system is. PE equals negative G, blah, 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 blah. So again, for using our units from before, here are the units in case you've forgotten. Note that it's still the distance is still measured in meters. Don't make that mistake again. And if we plug all these numbers in, we get that, we can just simplify this a little bit, and we get that the force is 7.62, okay, I don't want to read that whole thing. Let's simplify it. It's negative 7.363 times 10 to the 28. Yes, so there we go. So now you have learned what gravitational potential energy is and gravitational forces. So thank you for watching. Thank you for watching. Okay. If you like this video, subscribe and hit that notification bell so you never miss an upcoming update. And also, don't forget to hit the thumbs up button if you enjoyed it. Don't forget to share this channel with others, and see you next time.